why would I be shaking up a bottle of plain water?
I'm not sure, but...
You don't think it's plain water?
No, because of all the
bubbles in there.
Yeah.
And what's inside, you know? Water and what?
Type of gas.
Yeah, carbon dioxide gas. So you want to open that slowly? I'll get the towel ready. Yeah. So you can see there's a lot of gas dissolved in the water, okay?
Yes.
Well, here's another kind of water that has gas dissolved in it. Here, you want to wipe your hands off a little bit?
Sure.
I don't know whether you've ever had a chance to play with this, but if I tell you that it smells, you don't want to put your nose right over the top because scientists always do it like this. You smell it?
Mm-hmm.
What is it?
I don't know, but it sure smells really strong.
Yeah. It's ammonia. This time ammonia gas is dissolved in water. And because ammonia a lot of ammonia will dissolve in just a little bit of water, we can make a famous ammonia fountain. And here's what we'll do. Here's a baby bottle, okay, and here's the nipple, which we're going to put on upside down. This is the way it normally is. We're going to turn it upside down so it goes like that. So we can do it like that.
Okay.
Then we're going to fill the bottle first with ammonia gas by taking the ammonia and putting it in this little frying pan, put some on the bottom, put the funnel on the top, then I want you to put the bottle over like that. So we fill the bottle with ammonia gas. So bring it over here. Oh, by the way, see that red liquid in there?
Yeah.
When we get it filled with water or ammonia, you bring it over here and turn the bottle upside down and put it in there, okay?
Sure.
Okay, add a little ammonia. Put the funnel in. Okay, you hold the bottle over the top. See, I have some tape on there, so that's sort of working as a pot holder. Okay, hold it nice and straight like that. I'll go get the baby nipple. Now, ammonia gas dissolves in water so quickly that once we get it filled with ammonia gas and we put the nipple on upside down like this, one little drop of water has to get in there, and then a lot of ammonia gas will dissolve in it. That's going to lower the pressure here. And outside pressure on the liquid, that red liquid over there, is going to force it up inside. What's the matter? You keep turning away.
The ammonia
that
gas.
ammonia is sure strong, isn't it? Well, that means we're heating it and getting it out of the water in the little frying pan. Let's leave it on there to get a good supply of ammonia. Then anyway, once we get a little bit of water in there and the ammonia gas starts dissolving in there, outside air pressure is going to push up and force some of that red liquid up. Should go all the way to the top through that little hole. And then the more water you get in, the more gas, right?
Yeah.
Okay? You know what to do now. What are you going to do?
You're going to take it off and you're going to put the nipple on, then put it over.
Put it over there.
Rod.
Are you ready?
Yep.
Okay. Okay, go ahead.
You're ready?
Okay, now no water is getting up in there yet, right?
Yep.
So if you tip it off to the side and I can squeeze it a little bit to get one little drop of water up in there. There it goes, see it?
Yeah.
See the water? It's all the way up the top.
It's hitting the top.
Right. That's because we're lowering the pressure by dissolving the ammonia gas in the water. You call it ammonia water, and your mother uses it to clean up stuff around the house. Probably never realized that it's plain old water with ammonia gas dissolved in it. See, I have a little pin sticking up on the Superball bar.
Oh, yeah?
So when you drop it, I want you to drop it with the pin sort of up like this.
Okay.
You've dropped the Superball before, haven't you?
Yep.
Now notice you probably didn't wear safety glasses when you did it, because you don't think it's particularly dangerous. But you wait, later on it might be. So go ahead, drop first just a plain Superball. How high does it go?
It just bounced 3/4 of the way when it did when I dropped it.
Yeah, sort of. Now why is that?
Because when you drop it down, it's got to have some to bounce up again.
Right, so it bounces up again because this is made of a very elastic material. Okay, now on that little pin I have on the red ball, I'm going to put a small green Superball.
Okay.
Go ahead, now drop it.
Oh, wow, when shooting off.
Okay, you want to get the green one?
Okay. There it is.
Okay, wait till I pull the pin out, okay. Now stick it back on there again. Okay, now, why did that happen, do you suppose?
Well, since there's a bigger mass in the red ball, the energy was changed to the green ball, and it has a smaller mass, so it's got to have more speed.
Right, so when you drop it, most of the energy is transferred.
Yeah.
Okay, now this time, drop it again, but watch what happens to the red ball. What should happen, do you think?
Well, the energy is transferred to the green ball, so the green ball should have most of the energy, and the red ball wouldn't have very much.
Very much. Okay, so not much had happened to it. Okay, try it.
Okay.
It bounced only about that high, right? Okay, well here, take both balls and practice. And if you throw them from a higher distance, they'll go real high. Spiders spin webs of fine silk to catch insects. The finer the strands, the less chance an insect will spot them. Why then has this spider placed an obvious zigzag pattern at the center of its web? Thomas Eisner and Stephen Nowicki asked the same question. They found that birds often break the web by flying through it, which means the spider has to repair it. The scientist also found that birds more often were able to avoid a web with a zigzag pattern. That's probably why the spider put it there. Shan, I have a real challenge for you today
Okay.
that could have serious, dire consequences.
Oh.
And that is, here's a fruit drink, and it needs a teaspoon of sugar,
Okay.
and then you're going to have to drink it. But I'm not going to tell you whether sugar is an A or B, and you're going to have to determine which is which and put a whole teaspoon in there. Now, in order to do that, you're going to have to assume that salt and sugar have certain properties. How would you describe sugar? What is the property of sugar?
It's sweet.
Sweet, right. And the property of salt?
It's salty.
Salty, right. Those, note by the way, are properties that you can tell by tasting. But you can't taste in this case because we're going to assume that salt is a deadly poison.
Okay.
So you can't taste it. That's how you'd identify them around the house if there were a question, right?
Yeah.
So you have to find some other properties of these various materials in order to identify them. First of all, take a close look at them. Can you tell by just looking?
Well, by just looking at it, I would say that A is salt and that B is sugar.
B is sugar. Why? Just because you've seen salt and sugar before and you think? Well, scientists do the same thing, but they put it under the microscope and look at it very carefully,
Right.
especially the crystal structure. So come
Okay.
over here. I have a projector set up. There's the screen up there. And notice it says A and B. Okay. There's the two materials.
This looks like salt. It's bigger than
Yeah.
over here.
And the shape?
Yeah. These look like they're cubes. And some of them are rounder shapes. And these ones are all different kinds of shapes.
Right.
They're not really anything particular.
Okay, now let's look at this same sort of thing that, that scientists did over here in this chart. Scientists looked at the crystal structure of these two materials when they knew they were looking at salt. They said, okay, here's some salt. They looked at it, see what it says, crystal cubic. And you found those in A were cubic, right?
Yeah.
Actually, they look squares,
Yeah, they do.
because when you look at the top of a cube, it's a square. And sugar, monoclinic, that's a different kind of crystal structure. The important thing for household sugar, at least, is that they grind it up.
Right.
And that's what it looked like?
Yeah.
Okay. So now we have to look at some other properties and see if you agree with what scientists found.
Okay.
You know what solubility is?
Yeah, that's how much will mix into us
Right,
to water.
especially in water, okay. Notice salt.
39 grams, and in sugar, 500 grams. Boy, that's a big
That's
difference.
quite a big difference. So we should be able to use those two differences. Here are 2 spoons,
Okay.
2 glasses of water. Bring over A and B. And what's first? A.
A.
Okay. Put in maybe 2 heaping teaspoons. And I'll put 2 heaping teaspoons in over here, B.
Okay. Stir it around.
Let me trade. I know which is
Okay.
which, so I'd rather have you stir that one. Because that's the one you think is what? You think that's sugar, right?
B? Yes,
Yeah.
I think B is sugar.
Okay, well, we should be able to tell, I think, relatively quickly. Mine is
Mine is
staying
starting
cloudy.
to dissolve. It's going clearer.
Right. Does that sort of bear out what you found in the chart?
Yeah,
Solubility?
it does. Boy, it's almost clear now.
Yeah. And as you know, you can dissolve more and more until it finally gets syrupy, right?
Mm-hmm.
Yeah. So you still think B is sugar?
Yes, I do.
Then here's one final test that we will make while scientists would run all kinds of other tests.
Okay.
Notice the last one
Oh, the melting point.
in
Salt
Celsius.
in Celsius degrees. Salt doesn't melt till 801 degrees. Boy, is that ever hot.
Right.
And sugar, it starts to decompose at 160 degrees, a lot less.
Yeah.
And it chars,
and that's
it's the
down below. That's odor of caramel.
Oh,
I ran out
Okay.
of room. You know what that smells like? Okay.
yeah.
Well, let's try that. Light the
Okay.
candle. Okay. Here you are. See, there's a little piece of aluminum foil on a clothespin. You
Okay.
can put some of the stuff on there and hold it in the candle flame.
Okay,
So
this
first
is
A.
A.
Right? That's probably enough.
Nothing seems to be happening.
Well, the candle flame is probably not 800 degrees. It's only a
No.
couple of hundred degrees, yeah.
Yeah.
So that you suspect that that's salt?
Yeah, I do.
Okay, the final test.
Okay. Okay, here's some sugar, I think.
You think?
Yeah.
If it's sugar, what should happen?
It should
decomposes at
decompose.
160.
Oh.
Decomposing.
Yeah, it is.
Chars. Is
Uh-huh.
it charring? Turning black?
Yeah, it is. In some places.
And
I can smell some caramel, too.
yeah, okay. So you're definitely sure that sugar is B.
Yes, I am.
Okay. I will. You have to make a choice. You're sure?
I'm sure it's B.
Okay.
So
Heaping
put
teaspoon.
some in the drink. Okay.
And you have used the physical properties of materials in order to identify them in the same way that an analytical chemist does.
Yeah.
But you're going to do something which he would probably never do, or she, and that is test it by drinking it. But you are confident?
I'm ready.
Okay,
It was sugar that I put in.
great. Congratulations.
Thanks.
Finding better ways to prevent skidding on icy roads was the challenge confronting engineers at Pennsylvania State University. They found that sand spread over the ice begins to lose much of its effectiveness because as the tires continue to roll over the sand, it's scattered out of the way. But when they heated the sand in an oven and then spread it over the track, the hot sand melted the ice just enough for the grains to sink partway below the surface and then freeze in place, producing a lasting surface that's rough enough to keep vehicles from skidding. They also experimented with hot gravel. Watch as the ice melts around each stone. Heated materials that freeze into place on icy roads, a new method of skid control. Tarek, I'm stirring this solution with the end of a probe of the thermometer.
Yes.
And you know the temperature at which water boils, right?
Yes, it's 100 degrees Celsius.
Okay, well, there's what it is at the moment.
It's 106.
Yes.
How come?
Well, if I told you that we were going to eat this experiment by making this into chocolate, which we're going to pour over popcorn, will that give you a clue as to what's in here?
Oh, there must be something in it.
Yeah.
Doesn't look like chocolate or
No.
anything. Maybe sugar?
Right, sugar. In fact, what we're going to
Yes.
do is actually make a form of fudge. But now, first of all, we have to understand why is the temperature at 107.2, 107.1, and so forth, when it's supposed to be 100, right?
Yes.
Well, come on over here and see if I can show you. This is my version of a stove. Here's the
Okay.
burner over here, and here's the control. You can turn
Yes.
it on down here. In here at the moment, I have red balls that represent water molecules.
Okay.
So go ahead, turn on the burner and try to get some of the water molecules to jump up here, which would be similar to boiling. Okay, go ahead.
yeah.
Okay, turn it off right there. Now I turned it off and kept the burner at the same height, right? Same
Yes.
temperature. Because here are white balls which represent sugar molecules. You want to pour those in there?
Sure.
Okay, now when you turn it on, what should happen?
Well, the sugar molecules are big and they'll probably block the water molecule.
Yeah, they'll get in the way, right? So they have to. So that
Yes.
means in order to make the solution boil, what are you going to have to do to the temperature?
I'll have to turn it up.
Turn it up from 100 to 106, 107, right? Turn it
Yes.
on once. Turn it up. Okay. Very good. You got the idea now.
Yes.
When they're, by the way, here's the popcorn that we're going to pour the chocolate over. And let's take a look at what do we got here now?
Oh, it's about 109.
110. Okay. What I'd like you to do is to add a heaping tablespoon of cocoa.
Okay.
And I'll get ready to stir. Okay. Here, you want to put that around the back over there?
Okay.
Now, if a cook were going to do it without a laboratory thermometer like I have, they would cook this to hardball, which means they'd stir it and then they'd drop a little piece of it into some water. And when they put their finger in it, they could feel it was hard, then they would know it was finished.
That's interesting.
Yeah. Okay, Tarek, we're ready to pour it over the popcorn.
Okay.
Come on over here and stir it up. Make sure you get the stuff on the bottom all over. Okay?
Okay.
Because what you're trying to do is to get each one of the kernels of popcorn covered with, basically what we've made is sort of fudge.
Yes.
Have you ever had chocolate popcorn?
No, but I've had caramel popcorn.
Same idea.
Yes.
They're covering it, and this, by the way, the temperature when they're cooking that solution is also higher.
Yes, this smells really good.
Oh, thank you. Here, can I help? Just a
Okay.
minute. The reason why I can do this is, as a child, we had this at home an awful lot, and I made a lot of chocolate popcorn.
Oh, yes.
Okay. Now, as you stir it up like this, it not only will cool off, but it also will now get sugary, and that's where it's sort of like fudge.
Yes.
Just a little warm yet, but here, try that one right there. Careful, it might be a little warm. Well, what do you think? Hot, huh? Mm-hmm. Okay, now it's a little cooler. Try another one.
I never knew you were a great chef.
Well, thank you very much for the compliment, but that's about the only thing I cook. It's chocolate popcorn. And what is the temperature of boiling water? And there's something dissolved in it?
Well, it's 110 or 120, but it really depends on how much sugar is added to the water.
Or whatever the other chemical is dissolved in it.
Yes.
Certainly changes the boiling point. Very good. Okay, take it home. Give it to your friends.
Okay.
Shan, see this is a mantle from a lantern, you know, the gas lantern that you use for camping and stuff. Well, it's sitting here under a Geiger counter, and
What does that do?
and the radioactive indications that it picks up are sent over here to the computer, and it's counting them.
Oh,
How many
I see.
radioactive particles go through the end of the probe? Notice what we're reading there?
Yeah, 8, 6, 12, 14,
Okay.
8.
That's because this mantle is radioactive. Watch what
Oh.
happens when I take it away.
It drops to 0. Because there are no radioactive waves coming
Well,
out.
sometimes it might go to 1 or 2 because from sources outside of the solar system, cosmic rays are coming in, or some from the sun as well, come in and they're going through you and through me and through houses and whatnot, and every once in a while one goes through the probe.
Oh, okay.
And also radioactive stuff in the earth sometimes send background count And so we may get 1 or 2 there, but right now it's at 0, right?
Yeah, that's
Okay,
0.
before you leave today, you are going to identify what radioactive material is in that mantle.
How do you do that?
Well, you do that by, first of all, let's move that out of the way. Here are known radioactive sources, alpha, beta, and gamma. Okay? And if you put that, they're man-made so that we know they're only giving out one kind of radiation, an alpha, an alpha particle. So put that alpha particle underneath the probe of the Geiger counter.
It
Not
doesn't
much,
really do
right?
anything at all.
Now pick it up and hold it a little closer.
Oh, it starts at 238,
Yeah.
250.
Okay, now put it back down again.
And it drops to 0
Now
again.
what we're trying to do is find out what it is that stops the radiation. What was that stopped the radiation here?
Just the air.
The air, right. So anytime alpha particles are given off, the air alone, the molecules in the air are enough to stop them. Okay, now
Okay.
try the next one. Beta.
Beta. That's up to 32, 30, 44.
Obviously go through the air, right?
Yeah, the
Okay.
air doesn't stop that one.
Okay, now there's some lead sheets over there.
Okay.
Take one of them and put it over the top of the beta.
That stops it.
Right.
So the beta can go through air, but it can't travel through lead.
Right. And some other things it'll go through things like plastic and paper and stuff, but lead definitely will not go through. Okay? Try the next one now.
The gamma. 14, 12, 16, and the lead sheet doesn't do anything. It still keeps going.
No. Try another one.
Nothing.
How many do you got? 3 or 4?
Yeah, nothing stops that.
Keep going. You can see that the gammas are the most powerful, right?
Yeah.
They're not going to go through air, but one sheet, but all those sheets of lead they're going through.
Yeah.
Now, have you heard any place where they use radioactivity?
Well, I've heard something about cancer, but I don't know what they use them for or how they use them.
Well,
or anything.
the radiation, especially the gamma radiation, is harmful to cells because the radiation goes in and destroys part of the cell, so it kills it. So they use that to treat cancer. By very carefully focusing on parts of the body, they can fire the gammas in there, and that is the treatment for cancer. In skin cancer, they use beta, and you can see why.
Yeah,
because
it's not as strong.
So now you've seen the 3 different types of radiation. By the way, some natural materials might have all 3 or 2, but these, I say, were pure. So
Right.
now you should be able to identify the radioactivity in the mantle.
Well, I'll put a lead sheet over
What about
top
air?
of it. Well, the air doesn't stop
Right.
it, so
One
it can't
lead
be
sheet.
alpha.
Okay.
That stops it, so it can't be gamma. It must be beta.
Right, it must be a beta. Very good. Well, congratulations. For the first time, you've used the Geiger counter to identify an unknown radioactive substance by determining what kind of radioactivity it gave off. Very good.